Hello, I'm Roddy from Codasip, and the subject of this video is what is processor complexity. This is part of a series of 7 videos where we're considering things around the expanding Codasip RISC-V processor portfolio. So the previous one looked at what is processor performance, what we mean by that. We're now going to look into what we mean by processor complexity. Well, the complexity you need varies from application to application. So there are a number of things to consider. There's word length and registers, execution units, pipeline depth and latency, privilege and protection, and also virtual memory. So let's look into each of these categories briefly. Well, word length is an obvious one. Generally, the longer the word length, the larger the core, because the data path is wider if you've got a larger word length. However, there are corner cases where this does not necessarily apply. So, for example, some 8-bit cores like 8051 have similar areas to really small 32-bit cores. In fact, in such cases, the power consumption and code density may be much worse in the 8-bit core than a similar-sized 32-bit core. This is because more memory accesses are required and more clock cycles are needed to complete a computation. With growing word length, you may see some growth in the instruction set as well, which will add a little more complexity. So if we look at the RISC-V base instructions, with 32 bits, there are 47 instructions. With 64 bits, there are 59 instructions. And with 128 bits, 72 instructions. Another thing to consider with RISC-V, if you're doing 32 bits, is the number of registers. If you use the RV32I base instructions, you have 32 32-bit registers, whereas with RV32E, you have 16 32-bit registers. Let's now move on to execution units. This is obviously quite a simple treatment when not looking at the whole core, but fundamentally, if you are executing a single thread, the simplest case is that that thread issues a single instruction to the ALU. Now, sometimes, if you've just got a simple ALU, you may find that computations such as multiplication or division take too long. So it's common to add hardware multipliers or hardware dividers. Similarly, if you have intensive floating point computations, you'd want to put in a hardware floating point unit. And maybe you have some special computations where you've got computational bottlenecks that you'd like to address by extending the instruction set. You can create a more complex processor with additional custom instructions. That would be a typical application for using RISC-V. Now we can go beyond one ALU. If we look at the case of a single thread working with a superscalar core, the illustration here shows a dual issue core. You can simultaneously issue instructions to both ALUs. This is instruction level parallelism. Now, this will give you performance gains. But with this dual issue approach, if one thread stalls, then both ALUs may be idle. What is possible with a little more complexity is to have dual hardware threads. In this case, the threads are executed in parallel, with one ALU dealing with one thread and the other on the second ALU. Western Digital with their Swerve Core EH2 have shown that they can get close to the ideal 2x performance compared with a single execution unit. Another issue to consider is pipeline depth and latency. With a shorter pipe, you have lower latency. This means you can respond rapidly to interrupts. You have more logic, though, between stages, which will mean that your maximum clock frequency will be lower. However, this may be desirable in some applications, especially low-power ones, and you may actually end up with, on some occasions, with high performance per megahertz. With a longer pipeline, a consequence is high latency, which means a slower response to interrupts. It means less logic between stages, but you can achieve a higher maximum clock frequency. And you can end up with higher performance per second. Another area to consider is privilege and memory protection. Processors will always have one or more privilege modes. Machine mode is present in every single processor, and the RISC-V ISA defines machine hypervisor, supervisor, and user, although the hypervisor is not yet finalized. With machine mode, you have full access to the processor and memory hardware. It's unprotected access. It's just like root access in Linux. So the software you're running in machine mode must be completely trusted. User mode is aimed at normal, or if you like, untrusted applications, which are run with appropriate protection, so with less rights. And then supervisor mode has more rights than normal applications, but does not have the full access that machine mode has. Now, particularly with untrusted applications, you may want to protect the memory segments that are accessed. So physical memory protection will divide the memory into segments and stop unauthorized memory accesses. Then, finally, do you need virtual memory? This is used with more complex operating systems like Linux. And basically, the CPU works with a virtual address space and assigns this space to processes. So the physical memory is divided into pages, and you require a memory management unit to translate virtual addresses to physical addresses. So you need the extra complexity of an MMU and, in many cases, a translation look-aside buffer to speed things up. So the MMU and TLB, they provide extra hardware complexity without actually improving the performance of the CPU. So if you're considering a processor for your SoC, some basic questions you need to think about. What word length is appropriate for your application? What execution units do you need for your system? Are you happy to live with latency as a result of having a deeper pipeline? What privilege modes and memory protection do you need? And do you need virtual memory? So, if you think through these things, you can work out the sort of complexity that you need. So if we go back to the current families of Codasip RISC-V offerings, let's consider a few more of these questions. If you're wanting single issue, 4 of the cores support single issue. But if you want dual issue, you need to go to the swerve core EH1 or EH2. EH2 actually supports 2 hardware threads. We offer a range of pipeline lengths, ranging from 3 in the Codasip BK3 to 9 in the case of the swerve core EH1 and EH2. So, if you want to consider privilege, every core, of course, will have machine mode. If you're looking for user mode, that's supported with BK3, BK5 and BK7. And if you need supervisor mode, because for example you need to run Linux, the place to go for is BK7. So the Codasip RISC-V processor offering gives you a wide range of choices, whether it's word length, whether it's computational units, whether it's pipeline length, privilege mode, or virtual memory. There is a wide range of choice available. Thank you for your attention, and we hope you'll join us for the next video.